Imagine a time when there was absolutely nothing. No stars, no planets, not even empty space. Then, in a blink so fast it makes a hummingbird's wings look sluggish, everything exploded into existence. That wasn't just a beginning, it was the beginning. The Big Bang. And in the next few minutes, we're going on a mind-bending journey through everything that's happened since. From the first wisps of gas to the mind-bogglingly vast galaxies we see today, we'll unpack the epic story of our universe, making sense of the cosmic chaos so you can finally understand what's out there and how we got here. The Cosmic Dawn. The universe, after its initial fiery birth, was a dark, featureless place. Imagine a vast, empty room, but instead of walls and furniture, it's filled with a uniform, cool fog of hydrogen and helium gas. This was the state of affairs for hundreds of millions of years. There were no stars, no galaxies, just this immense, quiet darkness stretching in every direction. It was the ultimate cosmic before picture. Then, something remarkable began to happen. Gravity, that invisible force that keeps our feet on the ground and the planets in orbit, started to do its thing. It gently, but persistently, pulled clumps of this primordial gas together. These clumps grew larger and denser. Think of it like dust bunnies forming under your bed, except on an unimaginable scale, and instead of dust, it was the very building blocks of everything. As these gas clouds collapsed, the pressure and temperature at their centers began to skyrocket. Eventually, after an eternity of waiting, the conditions became just right for nuclear fusion to ignite. This is the same process that powers our sun, where hydrogen atoms smash together to form helium, releasing an incredible amount of energy. The first stars were born. These were giants, much bigger and brighter than our sun, and they burned hot and fast, living short but spectacular lives. These newborn stars, scattered across the cosmos, began to illuminate the darkness. This marked the end of the cosmic dark ages and the beginning of what astronomers call the cosmic dawn. It wasn't a sudden flash, but more like a slow sunrise. These early stars, clustered together in nascent galaxies, started to ionize the surrounding neutral hydrogen gas, clearing the fog and making the universe transparent to light. It was the universe's first real light show, a pivotal moment that set the stage for everything that followed, including the formation of all the stars and galaxies we see today. The first light. Imagine the universe a mere 380 years after its explosive birth. It wasn't the starry expanse we see today, but a dense, steamy fog. Think of it like a thick cloud of bathwater steam, so opaque you couldn't see your hand in front of your face, let alone a distant galaxy. This cosmic soup was a chaotic mix of charged particles, electrons zipping around like hyperactive toddlers, and protons, their much larger, more laid-back parents. Light, the ultimate speed demon, couldn't travel far without bumping into these charged particles, getting scattered and absorbed, much like a flashlight beam getting swallowed by fog. It was a universe that was literally in the dark, not because there was no light, but because the light couldn't escape. Then, something remarkable happened. The universe cooled down. As it expanded, it lost some of its fiery temper. This cooling allowed the protons and electrons to finally settle down and get together, forming neutral atoms, mostly hydrogen and helium. It was like the bathwater finally cooled enough for the steam to dissipate, revealing what was behind it. Suddenly, the universe became transparent. The photons, those little packets of light energy, were set free. They could finally travel in straight lines, unimpeded, across vast cosmic distances. This moment is what astronomers call the first light, or more technically, the era of recombination. These liberated photons are the oldest light we can possibly detect. They've been traveling through the universe ever since, stretching and cooling as the universe continued to expand. Today, we detect them not as visible light, but as faint microwave radiation, a sort of cosmic afterglow. It's like finding an old, faded photograph from a long-lost relative. It's not as vibrant as it once was, but it carries an incredible story. This ancient light, the cosmic microwave background radiation, is our window into the universe's infancy, a snapshot of that pivotal moment when the fog finally lifted, and the cosmos began to reveal its wonders. It's the universe's baby picture, and it tells us so much about where we came from. The Dark Ages. After the initial fiery birth of the cosmos, a period of profound quiet descended, a time so devoid of light that we astronomers affectionately, or perhaps ironically, call it the Dark Ages. Imagine the universe after a massive fireworks display, where all the dazzling explosions have faded, and you're left with just the lingering smoke and the faint, distant glow of embers. This was our early universe, a vast, dark expanse, not because there was anything inherently gloomy about it, but because the universe hadn't yet figured out how to turn on its grandest light bulbs. It was a cosmic nursery, still settling down after the Big Bang, a time when the building blocks of everything we see today were just starting to coalesce. Think of it like a freshly baked cake, still cooling in the oven. The ingredients are all there, mixed and ready, but the delicious aroma and the golden brown crust haven't appeared yet. In our universe's case, the ingredients were hydrogen and helium gas, the simplest elements forged in the Big Bang. These gases, spread thinly throughout the immense darkness, were the raw material for the first stars and galaxies. Gravity, that persistent cosmic sculptor, was slowly, patiently at work, tugging these gas clouds together. It was a slow dance, a gravitational waltz that took millions of years, drawing matter into denser and denser clumps. Eventually, in the densest pockets of gas, the pressure and temperature became so immense that a remarkable event occurred: nuclear fusion ignited. This is the cosmic equivalent of striking a match in a dark room. The very first stars were born, blazing beacons in the blackness. These were not your everyday stars, they were giants, hundreds or even thousands of times more massive than our sun, burning incredibly hot and bright. They lived fast and died young, their immense lifespans measured in mere millions of years, not billions. When they met their spectacular ends in colossal supernova explosions, they cooked up heavier elements, like carbon, oxygen, and iron, the very stuff we, and our planet, are made of. This was the end of the true dark ages, the universe finally beginning to illuminate itself, one stellar explosion at a time. The first stars ignite. Imagine a universe that's mostly dark, a vast, empty canvas stretching out in every direction. This wasn't always the case, though. After the Big Bang, the universe was a hot, dense soup of particles. As it expanded and cooled, these particles began to clump together. Gravity, that invisible force that keeps our feet on the ground and planets in orbit, started its slow, patient work. It pulled together clouds of hydrogen and helium, the simplest elements, like a cosmic baker kneading dough. These gas clouds were enormous, stretching for light years. Inside the densest parts of these colossal gas clouds, a remarkable transformation began. The immense pressure and heat generated by gravity were enough to force the atoms of hydrogen to fuse together, creating helium. This process, nuclear fusion, is like a tiny, perpetual explosion happening at an atomic level. When this fusion kicked in, it released an incredible amount of energy in the form of light and heat. Suddenly, after billions of years of darkness, the first stars flickered into existence, piercing the cosmic gloom like celestial birthday candles. These pioneers of starlight were unlike anything we see today. They were giants, far more massive and much hotter than our familiar Sunday. Think of them as the supermodels of the stellar world, all flash and fire, burning through their fuel at an astonishing rate. Because they were so big, their lives were incredibly short by cosmic standards, burning brightly for only a few million years before exploding in spectacular supernovae. These explosions were crucial, however. They scattered heavier elements, forged in the star's fiery cores, out into the universe. These elements, like carbon and oxygen, were the building blocks for future stars, planets, and eventually, life itself. Without these first, brilliant, and short-lived stars, the universe might have remained a much simpler, darker place. Galactic Genesis. The universe began as a scorching hot, incredibly dense speck. Think of it like a tiny, supercharged popcorn kernel, packed with all the ingredients for everything that would ever exist. Then, in an instant, it exploded outwards in an event we call the Big Bang. It wasn't an explosion in space, but rather an explosion of space itself, stretching and expanding at an unbelievable rate. Imagine blowing up a balloon, the surface expands, and dots drawn on it move further apart. That's kind of what happened, but on a cosmic scale. As this superhot soup of energy and particles cooled, things started to clump together. Gravity, the universal hugger, began its work. It pulled tiny bits of matter, mostly hydrogen and helium, the simplest elements, into denser regions. These weren't galaxies yet, more like vast, diffuse clouds. Picture a foggy morning, everything is spread out and indistinct. These primordial clouds were the building blocks, slowly gathering their strength. Over millions of years, these gas clouds collapsed under their own gravity. As they squeezed together, the pressure and temperature at their cores became immense. It was so hot and dense that atoms started fusing, creating heavier elements and releasing tremendous amounts of energy. This is how the very first stars were born, like cosmic campfires igniting in the darkness. These early stars were giants, burning brightly and quickly, forging the next generation of elements within their fiery hearts. They were the universe's first alchemists, turning simple ingredients into more complex ones. These massive stars lived fast and died young, often in spectacular explosions called supernovae. These explosions scattered the newly created elements, carbon, oxygen, iron, and more, back into space, enriching the surrounding gas clouds. This enriched material then became the birthplace for subsequent generations of stars and, crucially, 4 planets. Our own Sun and Earth are made from the star dust of these ancient stellar ancestors. It's like a cosmic recycling program, where the remnants of dead stars are used to build new celestial bodies, including us. The cosmic web forms. Imagine the universe as a giant, mostly empty room. Now, picture tiny specks of dust, too small to see, floating around. These specks are like the early bits of matter in the universe. For a long time, they were pretty evenly spread out. But gravity, that invisible force that keeps your feet on the ground and your coffee mug from floating away, started to work its magic. It's like a cosmic game of hide and seek, where the slightly bigger dust specks started to attract the smaller ones. Over millions and billions of years, this subtle attraction caused matter to clump together. It wasn't a sudden explosion, more like a slow-motion gathering. Think of it like a huge, cosmic knitting project. Gravity pulled threads of gas and dark matter closer and closer, forming thicker strands and leaving vast, empty spaces in between. These thicker strands are the beginnings of what we call the cosmic web. It's not a web spun by an arachnid, of course, but a vast, interconnected network of matter that fills the universe. These strands aren't just random lines, they are the highways of the cosmos. Galaxies, those enormous collections of stars, gas, and dust, tend to form along these dense filaments. They're like cities popping up along major trade routes. The emptier regions, where matter is scarce, are called voids. They are the quiet, sparsely populated countryside between the bustling cosmic cities. This structure, with its dense filaments and vast voids, is the large-scale architecture of the universe we observe today. It's a testament to the persistent, gentle pull of gravity over immense stretches of time. The Milky Way's infancy. Our galaxy, the Milky Way, began as a rather messy, sprawling cloud of gas and dust. Think of it like a giant, cosmic fog bank, but instead of water vapor, it was mostly hydrogen and helium, the simplest elements forged in the Big Bang. This primordial gas wasn't evenly distributed, there were denser pockets and sparser regions, much like how you might find thicker and thinner patches in a cloud of smoke. Gravity, that ever-present force, started to pull these denser patches together. It's a bit like how crumbs on a table might slowly gather into a pile if you nudge them around. These early clumps of gas weren't just passively waiting to be squished. Within them, tiny fluctuations in density, perhaps caused by shock waves from ancient, long-gone exploding stars, acted as seeds. Gravity then worked its magic, slowly but surely drawing more and more material into these growing pockets. It was a slow dance, a cosmic ballet of attraction and accretion. Over millions of years, these collections of gas and dust began to spin, just like water going down a drain. This spinning motion is crucial, it helped flatten the growing structure, setting the stage for the disc-like shape we associate with galaxies today. Imagine a pizza dough being spun and stretched, gravity was the hand doing the stretching, and the spinning helped it become a flatter disc. At this nascent stage, the Milky Way was far from the majestic spiral we see now. It was likely more of an irregular blob, a proto-galaxy still in the process of formation. Smaller clumps of stars and gas, much like tiny villages joining a growing city, were being gobbled up by the main mass. These mergers were violent affairs, stirring up the gas and igniting bursts of star formation. So, while our galaxy was still a toddler, it was already a busy, dynamic place, constantly growing and changing through these cosmic collisions. It was a bit like a construction site, with materials being brought in and structures being built, all under the watchful eye of gravity. Supermassive black holes emerge. The universe, in its infancy, was a rather chaotic place, a cosmic nursery filled with gas and dust. And from this primordial soup, something truly mind-boggling began to form, supermassive black holes. Think of them as the universe's ultimate vacuum cleaners, so dense that not even light can escape their gravitational pull. These behemoths, millions or even billions of times the mass of our Sun, didn't just pop into existence fully formed, their origins are still a bit of a cosmic mystery, but scientists have some pretty cool ideas. One leading theory suggests that these giants started as smaller black holes, perhaps born from the collapse of the very first stars. These early stars were massive, much bigger than our Sun, and when they died, they imploded, leaving behind a black hole. Then, like a snowball rolling down a hill, these smaller black holes began to gobble up surrounding gas, dust, and even other stars. Imagine a tiny pebble starting to attract more pebbles, then rocks, then boulders, until it's a giant boulder. That's kind of what happened, but on a cosmic scale, and with much more dramatic consequences. Another possibility is that huge clouds of gas, the kind that existed in the early universe, collapsed directly into black holes. These weren't just any clouds, they were gargantuan, spanning hundreds of thousands of light years. If you tried to imagine the size of one of these clouds, it's like trying to fit the entire Milky Way galaxy into a single, massive puff of smoke. When these colossal gas clouds collapsed under their own gravity, they could have formed black holes that were already quite substantial from the get-go, skipping the whole baby black hole phase. These supermassive black holes are not just cosmic curiosities, they play a crucial role in how galaxies form and evolve. They sit at the center of most large galaxies, including our own Milky Way. Their immense gravity influences the orbits of stars and gas within the galaxy, and the energetic jets they can spew out can either fuel or quench star formation. It's like the conductor of an orchestra, setting the tempo and influencing the entire performance of the galaxy. Without them, galaxies might look very different, perhaps more spread out or less structured. The first galaxies collide. The infant universe, still a cosmic toddler, was a much more crowded place. Galaxies, the vast island universes of stars, gas, and dust, were far more numerous and much closer together than they are today. Imagine a bustling city where skyscrapers are packed shoulder to shoulder, with very little empty space between them. This was the early cosmos. Gravity, the universe's persistent hugger, was constantly pulling these celestial neighbors towards each other. These early galactic encounters weren't gentle. Picture two colossal dust bunnies tumbling towards each other on a carpet, the collision would be messy. When galaxies merged, their stars, while incredibly unlikely to actually smash into each other, space is really, really big, would be flung into wildly different orbits. The gas and dust within them, however, were a different story. These clouds would be compressed, triggering furious bursts of star formation, like cosmic fireworks going off on an unimaginable scale. Some of these newly born stars would be massive, burning brightly and briefly before exploding as supernovae, seeding the cosmos with heavier elements. This galactic cannibalism, as some astronomers playfully call it, was a fundamental process in shaping the galaxies we see today. Our own Milky Way has a history of gobbling up smaller galaxies, and it's even on a collision course with the Andromeda Galaxy in the distant future, a cosmic rendezvous millions of years from now. These mergers weren't just about growth, they were about transformation. They helped to build up the larger, more structured galaxies, like the majestic spirals and elliptical giants that dominate the modern universe. It's how the universe went from a chaotic, crowded nursery to the more spread out, albeit still awe-inspiring, expanse we observe. The age of quasars. The universe, in its younger days, was a bustling metropolis, and the quasars were its neon signs. Imagine a time when galaxies were still figuring out their layout, and at the heart of many of them, supermassive black holes were having a cosmic feast. These weren't just any black holes, they were the gluttons of the early universe, actively pulling in vast amounts of gas and dust. As this material spiraled inwards, it got incredibly hot, like a cosmic kitchen on overdrive, and started shining with unimaginable brightness. These were the quasars, the universe's most luminous beacons. They were so bright that they could outshine their entire host galaxies, making them appear like tiny specks in the cosmic background. Think of it like finding a single, incredibly powerful spotlight in a dark stadium, making everything else seem dim by comparison. This era, often called the Age of Quasars, wasn't just about pretty lights. It was a crucial period for galaxy evolution. The intense energy blasting out from these quasars likely played a significant role in shaping the galaxies they lived in. It's like a cosmic windstorm, pushing gas around and potentially influencing how new stars were born. Some scientists believe these quasars might have even helped regulate the growth of their central black holes, preventing them from becoming too big too quickly. It was a delicate cosmic dance, with these energetic objects acting as both builders and regulators. So, what happened to all these blazing quasars? Well, as the universe aged, the fuel supply for these supermassive black holes dwindled. Galaxies matured, their gas reserves were either used up or dispersed, and the frantic feeding frenzy slowed down. It's like a popular restaurant eventually running out of ingredients or customers. The quasars, once the life of the cosmic party, gradually faded away. While we still see some active galactic nuclei today, they are nowhere near as numerous or as bright as they were during that ancient, energetic epoch. The universe, it seems, has calmed down considerably since its wild youth. The universe expands, accelerates. The universe isn't just getting bigger, it's doing so at an ever-increasing pace. This isn't some gentle, steady inflation like a balloon being slowly blown up. Instead, imagine you're watching a loaf of raisin bread bake. At first, the dough rises, and the raisins move apart. But then, as the yeast really gets going, the dough expands with more gusto, pushing those raisins away from each other faster and faster. That's a bit like what's happening with our universe. Scientists observed this astonishing acceleration by looking at distant exploding stars, called supernovae. These supernovae act like cosmic lighthouses, shining with a known brightness. By measuring how dim they appear from Earth, astronomers can figure out how far away they are. When they looked at the very furthest supernovae, they found that these cosmic explosions were farther away than they should have been if the universe's expansion was slowing down or even staying constant. It was as if the finish line kept moving further away while the runners were still trying to reach it. This discovery pointed to something mysterious pushing the universe apart, counteracting gravity's pull. This invisible force has been dubbed dark energy. Think of it like a hidden spring embedded in the fabric of space itself, constantly uncoiling and forcing everything outwards. It's a bit like trying to push two magnets together with their like poles facing each other. There's a force resisting you, trying to shove them apart. Dark energy is that cosmic shove, and it's winning the tug-of-war against gravity on the grandest scales. The implications are mind-boggling. If this acceleration continues, galaxies that are not gravitationally bound to our own Milky Way will eventually recede from us so quickly that their light will never reach us. They'll be like ships sailing over the horizon, disappearing into an ever-expanding darkness, forever out of sight. Our cosmic neighborhood might become a lot lonelier in the very, very distant future. It's a grand cosmic race, and it seems the expansion is winning. The formation of our solar system. Imagine a vast, swirling cloud of gas and dust, much like a cosmic fog bank, but unimaginably enormous. This wasn't just any fog, it was a nebula, the birthplace of stars and planets. Over countless eons, gravity, that invisible force that keeps our feet on the ground, began to pull this diffuse material together. Think of it like a snowball rolling down a hill, gathering more snow as it goes, but on a galactic scale. As more and more gas and dust clumped together, the center of this collapsing cloud got denser and hotter. Eventually, it became so incredibly hot and dense that nuclear fusion ignited, and voila, a star was born. Our Sun, a rather average star by cosmic standards, burst into existence in this spectacular fashion. But the story doesn't end with the Sun. Surrounding this newborn star was a flat, spinning disk of leftover material, like the rings around a cosmic record player. This protoplanetary disk was a chaotic place, filled with dust grains that bumped into each other. At first, these collisions were gentle, causing the dust grains to stick together, forming larger clumps. These clumps then collided, growing bigger and bigger, much like dust bunnies under your bed might eventually form a small tumbleweed. Over millions of years, these growing clumps, now called planetesimals, continued to collide and merge, sweeping up more and more material. Some of these planetesimals grew large enough to exert their own significant gravitational pull, attracting even more debris. These became the planets we know today. Near the hot Sun, only rocky and metallic materials could withstand the heat, leading to the formation of the inner, terrestrial planets like Mercury, Venus, Earth, and Mars. Further out, where it was much colder, volatile compounds like water ice and methane could condense, allowing for the formation of the gas giants like Jupiter and Saturn, and the ice giants Uranus and Neptune. These giants, with their immense gravity, then went on to influence the orbits of smaller bodies, gobbling up some and flinging others away, shaping the very architecture of our solar system. It was a cosmic game of billiards, played with rocks and gas, that ultimately sculpted the familiar neighborhood we call home. Earth takes shape. Picture this, our young Earth, a fiery toddler in the cosmic nursery. It wasn't always the cozy blue marble we know. Initially, it was a molten mess, a swirling cauldron of liquid rock and metal. Think of a giant, superhot pizza oven, but with elements far more volatile than pepperoni. This inferno was the result of countless asteroid and comet collisions, each impact adding more heat and material to the growing planet. It was a bit like a chaotic toddler throwing toys, but on a planetary scale, and with much more burning. As this superheated ball began to cool, something magical happened. Denser materials, like iron and nickel, sank towards the center, forming the Earth's core. Lighter elements floated to the surface, creating a primitive crust. This separation was crucial, like sorting laundry by color and fabric type, but with molten rock. Imagine a giant, slow-motion segregation of cosmic ingredients. This early crust was thin and unstable, prone to cracking and bubbling, far from the solid ground we walk on today. Then came the water. Huge amounts of water vapor, trapped within the molten rock, were released as the Earth cooled further. This vapor condensed, forming clouds so thick they would make a London fog look like a faint mist. Eventually, these clouds rained down, and it rained, and rained, and rained. For millennia, water poured from the sky, filling vast basins and creating the first oceans. It was a cosmic deluge, a planetary bath time that lasted longer than any of us could imagine. These early oceans were likely quite different from today's, perhaps warmer and more acidic, but they were the cradle of life. Life's humble beginnings. Imagine a primordial soup, not the kind you'd find at a diner, but a bubbling, chemical concoction stewing on a young Earth. This wasn't a place for a picnic, it was a cauldron of possibility. Simple inorganic molecules, like tiny Lego bricks, were zipping around, bumping into each other. Lightning storms, a common occurrence back then, provided the sparks, the energy needed for these bricks to start sticking together. Think of it like static electricity making your hair stand on end, but on a cosmic scale, causing chemical reactions. Over eons, these chemical reactions led to the formation of more complex molecules, the building blocks of life as we know it. These weren't quite cells yet, more like pre-cells, little oily blobs that could hold onto their internal soup and avoid mixing with the outside world. It's a bit like a tiny, self-contained bubble, a primitive form of privacy for these nascent life forms. Then came the breakthrough, self-replication. Suddenly, these blobs could make copies of themselves. It wasn't perfect, mind you. Sometimes the copies were a bit wonky, leading to variations. This is where the concept of evolution, the grand cosmic game of copy and paste with a few typos, really got its start. Those variations that were better at surviving and reproducing in the harsh early Earth environment were more likely to stick around and pass on their slightly improved blueprints. These early life forms were incredibly simple, probably more like a single-celled amoeba than anything you'd recognize today. They were single-celled organisms, tiny factories performing basic life functions. They didn't have eyes to see, or legs to walk, or even a brain to ponder the meaning of life, which, frankly, might have been a blessing back then. Their main goal was simple: eat, grow, and make more of themselves. And in doing so, they set the stage for everything that was to come, from the smallest bacterium to the largest whale, and eventually, to us humans who can now ponder how it all began. The Great Oxygenation Event. For billions of years, Earth's atmosphere was a bit of a snooze fest, chemically speaking. It was mostly nitrogen and carbon dioxide, with hardly any of the oxygen we breathe today. Think of it like a planet-sized, slightly pungent soup. Then, something truly revolutionary happened, thanks to some tiny, microscopic superheroes, cyanobacteria. These ancient microbes, essentially primitive algae, discovered a neat trick called photosynthesis. They figured out how to use sunlight, water, and carbon dioxide to make their own food, and as a fantastic byproduct, they released oxygen. It was like they invented their own personal air freshener, but on a global scale. At first, this oxygen was a bit of a problem. It reacted with all the iron dissolved in the oceans, forming rust. Imagine the ocean floor slowly turning into a giant, rusty bathtub over millions of years. This process locked away a lot of the early oxygen, preventing it from building up in the atmosphere too quickly. It was a sort of cosmic slow-release system. But eventually, all that dissolved iron got used up. The oceans were no longer a convenient oxygen sink. This is when things really heated up, or rather, got really oxygenated. The Great Oxygenation Event, as it's rather dramatically known, began. Suddenly, the oxygen produced by cyanobacteria started accumulating in the atmosphere. This was a massive environmental shift. For the anaerobic life that had thrived in the oxygen-free world, it was like a toxic gas attack. Many forms of life went extinct, unable to cope with this new, reactive gas. It was the ultimate hostile takeover, and it paved the way for new forms of life to evolve. This influx of oxygen changed everything. It allowed for the evolution of more complex life, including the ancestors of animals. Think of it as the universe going from a black and white silent film to a vibrant, noisy blockbuster. Our very existence, and the ability for anything larger than a microbe to breathe, is a direct consequence of these tiny, photosynthetic pioneers and their revolutionary waste product. It's a powerful reminder that even the smallest players can have the biggest impact on the grand stage of the universe. The rise of complex life. For billions of years, the universe was a rather dull place, mostly just gas and dust floating around, occasionally bumping into each other to make stars. These early stars were like the universe's first chefs, cooking up heavier elements, but life, well, it was still on the waiting list. Then, things started to get interesting. Planets began to form around these stars, and on at least one of them, Earth, the ingredients for something truly special started to mix. Think of it like a cosmic kitchen, where the right temperature, the right chemicals, and a whole lot of time were the secret recipes. Eventually, simple life forms, like tiny single-celled organisms, popped up. They were the universe's first tenants, and for a long, long time, they were the only tenants. They were like the solo artists of the biological world, doing their own thing. But then, a major upgrade happened. These simple cells started to work together, forming colonies. It was like a band deciding to jam together, and suddenly, they could do more. This collaboration led to the development of more complex cells, the kind that have little compartments inside doing different jobs, like tiny specialized factories. This was a huge leap, allowing for greater efficiency and more sophisticated functions. The real party started when these more complex cells began to organize into multicellular organisms. Imagine all those solo artists deciding to form a symphony orchestra. Suddenly, you had creatures with specialized tissues and organs, each doing its specific job. This allowed for a vast array of new forms and functions. We're talking about the ancestors of everything from the humble worm to the mighty whale. It was a period of incredible innovation, where evolution seemed to be experimenting with every possible design. Think of it as nature's ultimate design challenge, with billions of years to get it right. This explosion of complex life wasn't a smooth, immediate process. There were periods of rapid diversification, like a sudden boom in new product releases, followed by mass extinctions, which were like unfortunate recalls that wiped out entire product lines. But through it all, life persisted, adapting and evolving. The rise of complex life is a testament to the universe's ability to create intricate and beautiful systems from seemingly simple beginnings, a process that continues to unfold even now, with new species emerging and old ones adapting to a changing world. It's a story still being written, one cell, one organism, one ecosystem at a time. The Cambrian explosion. Suddenly, life on Earth decided to throw a massive party, and it was called the Cambrian explosion. Imagine a quiet neighborhood suddenly sprouting 100 new, wildly different houses overnight, each with its own bizarre architecture. That's kind of what happened about 541 million years ago. For billions of years, life had been mostly microscopic blobs, like single-celled organisms chilling in the primordial soup. Then, bam! A dizzying array of complex, multi-celled creatures appeared, seemingly out of nowhere. This wasn't just a few new species, it was a veritable explosion of new body plans. We're talking about creatures with hard shells, segmented bodies, and even the very first eyes, allowing them to see the world, and probably each other's weirdness, for the first time. Think of it as evolution hitting the fast-forward button. Animals like the trilobites, which look like ancient, armored wood lice, became the superstars of this era. They scurried across the seafloor, leaving behind fossilized footprints that tell us tales of their bustling lives. Other fascinating critters, like the Hallucigenia, with its spiky back and tentacle-like legs, or the Anomalocaris, a giant predator with formidable claws, also made their debut. It was a time of incredible biodiversity, a true renaissance for life. What caused this sudden burst of creativity? Scientists have a few ideas, like a surge in oxygen levels making it easier for larger, more active animals to thrive. Perhaps it was a genetic arms race. As some creatures developed better defenses, others evolved ways to attack, leading to a rapid diversification of traits. It's like a playground squabble that accidentally invents new toys for everyone. The oceans became a vibrant, competitive landscape, a far cry from the relatively peaceful microbial world that preceded it. This period laid the foundation for almost all animal life that exists today, a truly monumental event in our planet's history. The Age of Dinosaurs. For a colossal stretch of Earth's past, the planet was a very different place, ruled by giants. This was the Age of Dinosaurs, a period so long that trying to picture it is like trying to count every grain of sand on every beach. Think of it as the ultimate summer vacation for reptiles, but one that lasted for hundreds of millions of years. During this time, the land teemed with creatures we now only see as fossils or in movies, from the colossal, long-necked sauropods that munched on treetops like living skyscrapers, to the terrifyingly toothy Tyrannosaurus rex, the undisputed king of its domain. These weren't just big lizards, they were incredibly diverse, adapting to every conceivable environment, from lush, steamy jungles to arid, dusty plains. Imagine a world where a Brachiosaurus, so tall its head could peek into a second-story window, casually strolled past. Or picture a herd of Triceratops, like armored tanks with frills, grazing peacefully, their three horns a formidable defense against any predator. Even the smaller dinosaurs, like the speedy Compsognathus, darted through the undergrowth, hunting insects and small mammals, proving that size wasn't always the deciding factor. This era wasn't just about the big guys, it was a complex ecosystem where plants evolved alongside their giant herbivores, and smaller, often feathered, dinosaurs filled every ecological niche imaginable. It was a vibrant, dynamic world, a true testament to evolution's boundless creativity. These magnificent creatures dominated Earth for an astonishingly long time, far longer than humans have been around. They saw continents drift, climates shift, and mountains rise and fall. Their reign came to an abrupt and dramatic end, a cosmic event that wiped the slate clean, leaving behind only their stony legacies. But for millions upon millions of years, they were the undisputed rulers of this planet, a chapter in Earth's history so grand and awe-inspiring that it continues to capture our imagination today. Their story is a reminder of the incredible power of nature and the fleeting nature of even the most dominant life forms. The KPG extinction event. Picture this: 66 million years ago, Earth was a bustling place, full of incredible creatures, including those magnificent, giant lizards we call dinosaurs. Life was pretty good for them, roaming the land like kings. Then, bam. Something utterly catastrophic happened. It wasn't a slow decline, not a gradual warming or cooling. This was a sudden, violent end. The culprit. A colossal asteroid, estimated to be about 6 to 9 miles wide, decided to take a nosedive right into our planet. Imagine a mountain the size of Manhattan hitting Earth at speeds that would make a speeding bullet look like it was standing still. The impact site was near what is now the Yucatan Peninsula in Mexico, creating a crater so enormous it's hard to even fathom. This wasn't just a big rock, it was an apocalypse-level event. The immediate aftermath was pure chaos. The impact unleashed an energy equivalent to billions of atomic bombs. Think of a never-ending series of earthquakes and volcanic eruptions happening all at once, but on a global scale. Giant tsunamis, miles high, swept across continents, wiping everything in their path. Dust and debris were blasted into the atmosphere, shrouding the planet in darkness for months, maybe even years. It was like the ultimate lights out for the sun. Without sunlight, plants couldn't photosynthesize, which meant the herbivores starved. And if the herbivores are gone, guess what happens to the carnivores? Yep, they followed suit. This wasn't just a bad day for the dinosaurs, it was a global reset. About 75 of all species on Earth vanished. It was a brutal culling of life, a stark reminder that even the most dominant species aren't immune to the universe's sometimes violent surprises. But in the ashes of this devastation, new opportunities arose, paving the way for the evolution of creatures like us. The rise of mammals. The world changed dramatically after the big asteroid decided to play cosmic bowling with Earth. Suddenly, the reign of the dinosaurs was over, leaving a rather large, dinosaur-shaped hole in the ecosystem. This was the golden ticket for a group of critters who had been living in the dinosaur's shadow for ages: mammals. Think of them as the persistent understudies, always ready for their big break. These early mammals were mostly small, nocturnal, and a bit like furry little opportunists. They scurried around, nibbled on insects and seeds, and generally tried not to become a dinosaur's snack. They had a few advantages, though. Unlike their scaly overlords, mammals were warm-blooded, meaning they could keep their body temperature steady, like a built-in furnace. This allowed them to be active in the cool of the night, while the dinosaurs were snoozing. Plus, they nursed their young, giving their offspring a better start in life. It's like having a built-in daycare service, which, let's be honest, is pretty handy. When the dust settled from the asteroid impact and the volcanic eruptions that followed, the planet began to heal. With the giant reptiles gone, the stage was set for diversification. Mammals, those adaptable survivors, began to spread out and explore all the empty niches. Some stayed small and rodent-like, while others started to get bigger and bolder. This was the dawn of the truly diverse mammalian world we know today. Imagine a world where you don't have to constantly look over your shoulder for a T-Rex. Suddenly, there was room to grow, to experiment, to evolve into all sorts of shapes and sizes. This led to the development of everything from the tiniest shrew to the massive whales of the ocean. It was a slow, unfolding process, but essentially, the end of one era paved the way for the spectacular rise of the furry, the feathered, well, sort of, birds are also descendants, and the fantastic variety of mammals that now inhabit our planet. The evolution of humans. Our journey through the vastness of the observable universe, when narrowed down to the story of us, begins not with a bang, but with a slow, simmering change. Think of it like a pot of soup on the stove, where over a very, very long time, the ingredients transform. For us, those ingredients were simple organic molecules, floating around in the primordial oceans of early Earth, approximately 4 billion years ago. These molecules, under the influence of lightning, volcanic activity, and ultraviolet radiation, started to get a bit chatty. They bumped into each other, hooked up, and formed more complex structures, like amino acids, the building blocks of proteins. It wasn't exactly a party, more like a very slow, very messy chemical reaction. Fast forward a billion years or so, and these complex molecules started to get organized. They figured out how to make copies of themselves, a primitive form of reproduction. This is where we get the first true life forms, single-celled organisms, like bacteria. Imagine the simplest possible life you can think of, even simpler than a single amoeba in a pond. These microscopic marvels were the undisputed rulers of Earth for eons, just chilling in the water, doing their thing, completely unaware of the cosmic drama unfolding around them. They were the original inhabitants, the OG residents of our planet. Then, things started to get a bit more complicated, literally. Around 2 billion years ago, some of these single-celled organisms developed a neat trick: they could use sunlight to make their own food. This is called photosynthesis, and it was a game changer. It pumped oxygen into the atmosphere, which was basically poison to most of the life at the time. It was like someone opening all the windows in a stuffy room, making it fresh for some but unbearable for others. This oxygen revolution paved the way for more complex life, including multicellular organisms. These were the first animals and plants, a leap forward from single-celled simplicity to the beginnings of specialized cells working together. The really exciting stuff, for us anyway, kicked off much later, during the Cambrian explosion about 540 million years ago. Suddenly, life diversified like crazy. We saw the emergence of creatures with shells, exoskeletons, and backbones. Think of it as a massive biological startup boom. All sorts of weird and wonderful body plans appeared. Then came the dinosaurs, ruling the planet for an astonishing 165 million years. They were the rock stars of their era, big and powerful. But like all rock stars, their time eventually ended, making way for new acts. After the dinosaurs bowed out, mammals, which had been around for a while but mostly living in the shadows, began to diversify and fill the vacant ecological niches. This led to the evolution of primates, our more distant, tree-dwelling ancestors, who eventually gave rise to us, Homo sapiens. It's a long and winding road, from simple soup to sophisticated brains, a testament to the universe's slow, persistent drive towards complexity. The agricultural revolution. The shift from hunting and gathering to farming, known as the agricultural revolution, was a game-changer for humanity. Suddenly, people weren't constantly on the move, chasing down their next meal. Instead, they could settle down in one place and cultivate crops like wheat, barley, and rice. This was a pretty big deal, like deciding to get a dog instead of just petting other people's dogs. You're committing to something, and it's going to change your life. This settled lifestyle led to surplus food. Imagine having more apples than you could possibly eat in a week. This abundance meant not everyone had to farm. Some folks could specialize in other things, like making better tools, building more permanent houses, or even creating art. It was the beginning of societies with different jobs and roles, sort of like how a band has a drummer, a guitarist, and a singer, each doing their own thing but contributing to the whole. With more people living together and relying on farming, villages and eventually towns began to form. This concentration of people brought new challenges, like managing resources and dealing with disputes. But it also fostered innovation. Think about it, if you're stuck in one place with a bunch of neighbors, you're bound to come up with new ways to cooperate or compete. This led to the development of early governments and social structures, all stemming from the simple act of planting a seed and watching it grow. It was a slow process, not like flipping a switch, but the impact was profound, shaping the trajectory of human civilization in ways we still feel today. The dawn of civilization. The first whispers of civilization began not with a bang, but with a slow, deliberate cultivation. Imagine tiny seeds, carefully planted, nurtured, and then, a bounty. This was the dawn of agriculture, a monumental shift from the nomadic life of hunting and gathering. Suddenly, people could stay put, build permanent homes, and watch their families grow. It was like trading a fast food burger for a home-cooked meal, a lot more effort, but infinitely more rewarding in the long run. This stability allowed for the very first villages to sprout, like mushrooms after a spring rain. With settled life came specialization. Not everyone had to be a hunter or gatherer anymore. Some folks discovered they were rather good at making pots, others at weaving cloth, and a few, bless their souls, became leaders. This division of labor was a game changer. It meant that complex tasks could be accomplished, and new ideas could flourish. Think of it like a modern-day office, but instead of spreadsheets, they were managing irrigation, and instead of meetings, they were having really important discussions about where to build the next granary. It was the beginning of societies, where people worked together for a common good, or at least, for a common store of grain. These burgeoning communities needed ways to organize, to keep track of who owed what, and to ensure everyone knew the rules. This is where the earliest forms of governance emerged. Simple rules, perhaps agreed upon by the elders, evolved into more complex systems. And to manage all this, a need arose for record-keeping. This is the genesis of writing. At first, it was just simple symbols, perhaps tally marks on clay to count sheep, or little pictures to represent a harvest. It wasn't Shakespeare, but it was the foundation for everything from grocery lists to epic poems. The development of tools also played a crucial role. From sharpened stones to early metalworking, these innovations made life easier and more productive. Imagine trying to build a house with just your bare hands. It would be a lot slower and a lot more painful. These tools allowed for more ambitious projects, like larger buildings, more efficient farming, and even the beginnings of trade networks. It was a snowball effect. Better tools led to more food led to larger populations, and larger populations led to more complex societies, all while people were probably still arguing about whose turn it was to fetch water. The scientific revolution. The universe, once a realm of mystery explained by ancient philosophies and religious dogma, began to reveal its secrets through a period of intense scientific inquiry. This era, often called the scientific revolution, wasn't a sudden explosion but a gradual shift in how people thought about the natural world. Instead of relying solely on what ancient thinkers like Aristotle had said, scholars started looking at the sky, the planets, and everything around them with fresh eyes, armed with curiosity and a growing toolkit of mathematics and observation. Think of it like suddenly realizing that instead of just accepting what your grandma told you about how to bake a cake, you could actually try different ingredients, measure them precisely, and see what happened. That's what these scientists started doing with the cosmos. Figures like Nicholas Copernicus, though not directly part of the later revolution, laid crucial groundwork by proposing that the Earth wasn't the unmoving center of everything. His idea of a sun-centered solar system, while initially met with skepticism, planted a seed of doubt about established views. Later, Johannes Kepler, using meticulous observations, refined this heliocentric model, discovering that planets move in elliptical paths, not perfect circles. This was a huge departure from the ancient belief in celestial perfection. Imagine trying to draw a perfect circle around a point, only to find out all the planets were drawing slightly squashed circles instead. It sounds simple now, but it was a radical idea back then, demanding a new way of understanding cosmic mechanics. Then came Galileo Galilei, a true game changer. With his improved telescope, He looked at the moon and saw mountains and craters, proving it wasn't a perfectly smooth, ethereal sphere. He observed moons orbiting Jupiter, providing a mini-solar system that mirrored Copernicus's proposal. He even studied falling objects, showing that they accelerate, a concept that challenged centuries of accepted physics. Galileo's persistence in advocating for his findings, even when it put him at odds with powerful institutions, exemplifies the spirit of the revolution, a commitment to empirical evidence over tradition. He essentially said, let's not just talk about it, let's look at it and measure it. His work was like bringing a powerful new magnifying glass to the universe, revealing details no one had ever imagined. This period also saw Isaac Newton synthesize much of this new knowledge into a grand, unifying theory. His laws of motion and universal gravitation explained why apples fall to the ground and why planets orbit the sun with the same fundamental principles. It was an astonishing achievement, providing a mathematical framework for the universe that seemed to operate like an incredibly complex, yet predictable, clockwork. Newton's insights were so profound that they dominated scientific thought for centuries, offering a rational, mechanistic view of the cosmos that was both awe-inspiring and deeply influential, showing that the same rules applied everywhere, from a falling apple to the distant stars. The Enlightenment. The Age of Enlightenment, a period that dawned in Europe during the 17th and 18th centuries, brought a fresh perspective to understanding the cosmos. Think of it as a grand intellectual awakening, where people started looking at the universe not just with wonder, but with a burning desire to figure out how it all worked. This wasn't about magic or divine whispers, it was about using reason, observation, and logic, much like a detective solving a mystery. Scientists and thinkers of this era began to believe that the universe operated according to predictable, discoverable laws, not just random whims. They saw the intricate dance of planets and stars as evidence of an underlying order, a cosmic clockwork waiting to be understood. It was a time when questioning the established norms, even those handed down by ancient authorities, became not just acceptable, but celebrated. One of the key breakthroughs was the development of new tools and techniques for observing the heavens. Telescopes, once crude instruments, became more powerful, allowing astronomers to see farther and clearer than ever before. This meant they could spot new celestial bodies, meticulously chart the movements of existing ones, and begin to grasp the sheer scale of the universe. Imagine peering through a window that suddenly gets much, much bigger, revealing details you never knew existed. This era also saw the refinement of mathematics, providing the language and framework to describe these celestial mechanics. Equations became the universal grammar of the cosmos, allowing scientists to predict phenomena with astonishing accuracy. It was like finally finding the instruction manual for the universe. This intellectual ferment wasn't confined to dusty observatories or university halls, it permeated society. The idea that humans, through their own intellect, could comprehend the universe was incredibly empowering. It fueled a sense of optimism and a belief in progress. People started thinking about applying these principles of reason and order to human society itself, leading to new ideas about government, individual rights, and scientific inquiry. It was a ripple effect, where understanding the stars helped people understand themselves and their place in the grand scheme of things. The universe, once a distant and mysterious realm, began to feel a little more accessible, a little more understandable, thanks to the power of human reason. The Industrial Revolution. The hum of the cosmos, a faint whisper across unimaginable distances, carries with it the echoes of creation. From the initial fiery birth of stars to the slow dance of galaxies, the universe has been a grand, evolving spectacle. This ongoing transformation, this cosmic genesis and development, is what we call the observable universe. It's a vast, dynamic arena where matter and energy have been shaping and reshaping themselves for billions of years, leading to the intricate structures we see today. The Industrial Revolution, a period of immense technological and societal change on Earth, might seem a world away from the grand cosmic narrative. Yet, it marked a pivotal moment in humanity's ability to observe and understand that very universe. Before this era, our view of the stars was limited to what the naked eye could perceive, a beautiful but relatively simple panorama. Think of ancient stargazers, charting constellations based on patterns they recognized, like connect the dots in the sky. Their understanding was profound for its time, but fundamentally constrained. Then came the telescope. Suddenly, our cosmic vision was dramatically enhanced. Galileo's early spyglasses, when pointed skyward, revealed a universe teeming with previously unseen wonders, the craters on the moon, the moons of Jupiter, and the countless stars that make up the Milky Way. This wasn't just a fancier pair of binoculars, it was a revolution in perception. It was like upgrading from a blurry, black and white television to a high-definition screen, revealing details and complexities that were utterly imperceptible before. This burgeoning ability to see further and clearer directly impacted our understanding of our place in the cosmos, shifting us from a central, unique position to one amongst many celestial bodies. The advancements didn't stop there. The Industrial Revolution fueled further innovation in optics and mechanics, leading to bigger, more powerful telescopes. These instruments allowed astronomers to not only see more stars but to begin measuring their distances, studying their light, and even inferring their composition. It was during this time that humanity truly began to transition from simply looking at the universe to actively studying it. This period laid the groundwork for everything that followed, from understanding the nature of light itself to eventually grappling with the immense scale and age of the universe we inhabit. It was a giant leap for humankind's cosmic curiosity. The space race begins. The idea of reaching for the stars wasn't just a sci-fi dream anymore, it was about to become a very real, very competitive endeavor. Imagine two kids on a playground, both wanting to climb the tallest tree first. That's kind of what happened, but with rockets and superpowers. The United States and the Soviet Union, two global giants who had just finished a massive world conflict, found themselves in a new kind of showdown. This wasn't about armies clashing, but about who could build the biggest, fastest, and most impressive rockets. It was a race to prove technological superiority, a silent battle waged not with bullets, but with scientific ingenuity and sheer willpower. Think of it like a high-stakes baking competition, where each side is trying to create the most spectacular cake to impress everyone. The Soviets actually got a significant head start. In 1957, they shocked the world by launching Sputnik 1, the first artificial satellite. It was just a little metal ball, beeping away in orbit, but its impact was enormous. It was like someone suddenly appearing at the finish line of a marathon you thought you were winning. This tiny beep sent ripples of concern through the American public and government. Suddenly, the idea of Soviet rockets capable of reaching space also meant they could potentially reach anywhere on Earth. This sparked a sense of urgency, a feeling that America needed to catch up, and fast. It was a wake-up call, loud and clear, that the technological race was on. In response, the United States poured resources into its own space program. This meant a massive investment in science education, research, and the development of powerful rockets. It was like deciding to build a superpowered water balloon launcher after your neighbor's water balloon accidentally landed on your roof. The goal wasn't just to launch a satellite, but to surpass the Soviets. This led to the creation of NASA, the National Aeronautics and Space Administration, in 1958, consolidating various civilian space efforts. The competition intensified, with both nations striving to achieve new milestones, pushing the boundaries of what was thought possible. Every launch, every satellite, every scientific discovery became a point in this grand, cosmic game. The discovery of exoplanets. For ages, humanity has gazed at the stars, wondering if we were alone. It turns out, the answer is a resounding nope. The search for planets orbiting other stars, which we call exoplanets, is a relatively recent scientific adventure. Think of it like trying to spot a firefly next to a lighthouse from miles away, incredibly difficult, but not impossible. Early attempts were like shouting into the void, hoping for an echo. Scientists had theories, of course, but proving them was another story. It wasn't until the late 20th century that the first solid evidence started trickling in. The breakthrough came from observing the subtle wobble of stars. Imagine a dancer spinning around. If a dancer is holding a ball, the dancer will move a little bit as the ball orbits them. Similarly, a star might appear to wiggle slightly as an unseen planet tugs on it with its gravity. This tiny movement, a cosmic dance step, is what astronomers learned to detect. It's like noticing your car keys jiggling on the table because a tiny mouse is scurrying underneath. This indirect method, called the radial velocity method, was the first major tool in our exoplanet hunting arsenal. Then came a game changer, the transit method. This is akin to watching a distant streetlight blink off and on. When an exoplanet passes directly in front of its star from our perspective, it blocks a tiny bit of the star's light. This dip in brightness, however small, is a telltale sign of a planet's presence. It's like noticing the sun dimming for a split second as a bird flies across its face. Space telescopes, like Kepler and TESS, have been incredibly effective at spotting these subtle dips in starlight, allowing us to discover thousands of exoplanets. These discoveries have painted a picture of a universe teeming with worlds. We found gas giants bigger than Jupiter, rocky planets smaller than Earth, and everything in between. Some exoplanets orbit their stars so closely they're practically roasted, while others are locked in frigid darkness. The sheer diversity is astounding, proving that the universe is far more creative than we could have imagined. It's like opening a box of chocolates and finding not just the usual flavors, but entirely new, unexpected ones, each with its own unique characteristics. This ongoing exploration continues to expand our understanding of planetary systems and the potential for life beyond our own solar system. The search for extraterrestrial life. For centuries, humanity has gazed at the stars, wondering if we're alone in the vast cosmic ocean. This age-old question fuels the ongoing search for extraterrestrial life, a scientific endeavor that's become increasingly sophisticated. It's not just about finding little green men. Scientists are looking for any form of life, from simple microbes to advanced civilizations. Think of it like searching for a specific grain of sand on a beach, but the beach is the entire universe. Our search is guided by a few key ideas. We look for planets orbiting other stars, called exoplanets, that might have conditions suitable for life as we know it. This means finding planets in the habitable zone, where temperatures could allow liquid water to exist on the surface. Liquid water is considered crucial because it's the solvent for all known life on Earth, acting like a universal mixer for the ingredients of biology. Astronomers use powerful telescopes, like the Kepler Space Telescope and now the James Webb Space Telescope, to detect these distant worlds by observing the tiny dips in starlight as a planet passes in front of its star, or by measuring the wobble of a star caused by a planet's gravity. These methods are like trying to spot a firefly blinking near a distant lighthouse. Beyond just finding potentially habitable planets, scientists are also actively listening for signals. Projects like SETI, Search for Extraterrestrial Intelligence, use radio telescopes to scan the skies for any non-natural radio waves that could indicate intelligent life, sending out a cosmic hello. It's a bit like trying to pick up a specific radio station in a noisy city, hoping to hear a clear broadcast amidst all the static. While we haven't received any definitive signals yet, the sheer number of stars and planets in our galaxy suggests that the odds might be in our favor. If life arose independently on Earth, it's plausible it could have arisen elsewhere too. The quest also extends to exploring our own solar system. Missions to Mars, for instance, are searching for signs of past or present microbial life, analyzing rock and soil samples for organic molecules and evidence of ancient water. Even moons like Europa, a moon of Jupiter, and Enceladus, a moon of Saturn, are considered prime candidates due to the strong evidence suggesting they harbor vast liquid water oceans beneath their icy shells. These subsurface oceans could be teeming with life, hidden from our direct view but potentially accessible through future robotic probes. The discovery of extremophiles on Earth, organisms that thrive in incredibly harsh environments like deep-sea hydrothermal vents or highly acidic hot springs, gives us hope that life can exist in unexpected places, both here and potentially on other worlds. The Hubble Revolution. Before Hubble, our view of the cosmos was like trying to see a distant city through a thick, smoggy window. We knew there were stars, and we suspected there were other galaxies, but the details were fuzzy, like a poorly focused photograph. Edwin Hubble, a sharp-eyed astronomer, was one of the first to really push against those blurry limits. He used the enormous Hooker telescope in California, a giant eye staring at the sky, to observe nebulae that others had dismissed as mere clouds of gas within our own Milky Way. But Hubble had a hunch. He noticed certain stars within these nebulae that pulsed with a regular rhythm, variable stars called Cepheids. These stars are like cosmic lighthouses. Their brightness changes in a predictable way that's directly related to their true luminosity. Think of it like knowing that a certain type of street lamp always has the same wattage. If you see a dim one far away, you know it must be a great distance, and if you see a bright one nearby, it's obviously closer. Hubble used this incredible insight. By measuring how bright these Cepheids appeared from Earth and knowing their true brightness, he could calculate their distances. And what did he find? He found that some of these nebulae were so far away that they simply had to be entire galaxies, separate island universes floating in the vast ocean of space, much like our own Milky Way. This was revolutionary. It shattered the prevailing idea that the Milky Way was the entirety of existence. It was like discovering that your house wasn't the only building on Earth, but that there were countless other cities stretching out beyond the horizon, each with its own stars and planets. Hubble's observations, published in the late 1920s, fundamentally changed our understanding of our place in the universe, revealing a cosmos far grander and more populated than anyone had imagined. This opened the floodgates for understanding the scale and structure of the universe. Cosmic microwave background insights. That faint glow permeating the entire cosmos, the cosmic microwave background, is like an ancient baby picture of the universe. It's the leftover warmth from the Big Bang, a time when the universe was an incredibly hot, dense soup of particles. Imagine a room that's been heated up for ages. Even after you turn off the heater, it takes a long time for the room to cool down. The CMB is like that residual heat, but on a cosmic scale, and it's been cooling down for billions of years. Scientists can study this light, which is now mostly in the microwave part of the spectrum, hence the name, to understand what the early universe was like. It's like finding an old, faded photograph that tells us about our ancestors. What's really neat is that this background glow isn't perfectly uniform. There are tiny temperature variations, like minuscule ripples in a pond. These slight differences, incredibly subtle, are crucial. They represent areas where matter was slightly more or less dense in the early universe. Think of it like a loaf of bread dough rising, some parts puff up more than others. These denser regions eventually became the seeds for all the galaxies and stars we see today. So, those tiny temperature wobbles in the CMB are basically the blueprints for the cosmic structures we observe. It's a bit like looking at a chaotic pile of Lego bricks and realizing that the arrangement of a few key pieces determined where the entire castle would eventually be built. Studying these patterns in the CMB has allowed cosmologists to figure out a lot about the universe's composition. For instance, we've learned that the universe isn't just made of the stuff we can see, like stars and planets. A significant portion is actually made of dark matter and dark energy, mysterious components that don't interact with light. The CMB data is like a cosmic tax return, showing us how much of each ingredient went into the cosmic recipe. It's helped us estimate that about 5 of the universe is normal matter, about 27 is dark matter, and a whopping 68 is dark energy. Without the CMB, we'd be in the dark about these crucial, unseen elements. The precision with which we can now measure these CMB fluctuations is astounding. Satellites like COBE, WMAP, and Planck have mapped the sky with incredible detail. They've essentially taken high-resolution selfies of the early universe. These missions have helped refine our understanding of the universe's age and its expansion rate. It's like going from a blurry, black and white photo to a crystal-clear, high-definition video. Each improvement in our observational tools gives us a clearer picture of our cosmic origins and helps us test our theories about how everything came to be. Dark matter revealed. For decades, astronomers noticed something peculiar. Galaxies were spinning way too fast. Imagine a merry-go-round. If it spins too quickly, the riders would fly off, right? Well, galaxies seem to be defying this cosmic physics. The visible stuff, stars, gas, dust, just didn't have enough gravitational pull to hold them together at those speeds. It was like seeing a juggler keep an impossible number of balls in the air without any visible strings. This mystery pointed to unseen mass, a kind of cosmic glue holding everything together. This invisible stuff, which we've dubbed dark matter, doesn't shine, reflect, or absorb light. It's completely transparent to our telescopes. Think of it like trying to find a black cat in a coal cellar. You can't see it directly. We only know it's there because of its gravitational effect. It's the silent conductor of the cosmic orchestra, influencing how galaxies form, cluster, and move. It's not just a little bit of extra stuff either. Calculations suggest dark matter makes up about 85% of all the matter in the universe. Scientists have been on a quest to directly detect dark matter particles. Imagine trying to catch a ghost. Many experiments are set up deep underground, shielded from cosmic rays and other background noise, hoping to catch a faint interaction between a dark matter particle and a detector. These detectors are incredibly sensitive, designed to register the tiniest nudge. It's like setting out a super-delicate mousetrap hoping to catch a mouse that's almost entirely intangible. So far, definitive proof of a specific dark matter particle remains elusive, but the search is far from over. The implications of understanding dark matter are enormous. It's not just about filling a gap in our cosmic inventory, it's about understanding the fundamental building blocks of the universe and how it evolved. If we can finally identify what dark matter is, it could revolutionize physics, possibly leading to entirely new theories beyond our current understanding. It's like discovering a whole new color that we never knew existed, changing how we perceive the entire spectrum of reality. Dark energy's mystery. Imagine the universe as a giant, ever-expanding balloon. For a long time, scientists thought that gravity, like a bunch of tiny rubber bands, would be slowing down this expansion. It made sense, right? All the stuff in the universe, the stars, galaxies, even that embarrassing sock you lost under the couch, they all pull on each other. So, you'd expect things to slow down, maybe even eventually collapse back in on themselves. But then, in the late 1990s, astronomers looked at distant exploding stars, called supernovae, and got a shock. These supernovae were farther away than they should have been, meaning the universe's expansion wasn't just continuing, it was actually speeding up. It was like realizing your balloon wasn't just inflating, it was being actively blown up faster and faster by some invisible force. This mysterious something pushing everything apart is what we've dubbed dark energy. It's called dark because we can't see it, touch it, or detect it with any of our usual instruments. It doesn't interact with light, which is how we see most things. Think of it like the air in your tires. You know it's there, and it's essential for the tire to hold its shape and for your car to roll smoothly, but you can't see the air itself. Dark energy seems to be a property of space itself, becoming more dominant as the universe gets bigger. As the balloon inflates, there's more space, and therefore, more of this space stuff pushing outward. What exactly is this dark energy? That's the million-dollar question, or perhaps the trillion-trillion-dollar question, considering the scale of the universe. One leading idea is that it's a cosmological constant, a sort of inherent energy density of empty space, first proposed by Einstein but later dismissed by him. It's like a fundamental property of the vacuum, a perpetual motion machine of expansion. Another possibility is that it's a new kind of energy field, something we haven't encountered before, that changes over time. It's a bit like trying to figure out why your internet connection suddenly speeds up or slows down. There could be many reasons, some simple, some incredibly complex. The implications of dark energy are profound. If it continues to dominate, the universe will keep expanding at an accelerating rate. Eventually, galaxies will become so distant from each other that they'll disappear from our view, leaving our own galaxy isolated in a vast, dark expanse. It's a bit like being at a party where everyone is slowly and steadily walking away from you, until you're eventually alone in a room. Understanding dark energy is crucial for understanding the ultimate fate of the cosmos, and right now, it's one of the biggest puzzles in physics. It's a cosmic enigma that keeps scientists scratching their heads, searching for clues in the farthest reaches of space. The future of the universe. The universe's ultimate fate is a cosmic guessing game, but the leading theory points towards a scenario of eternal expansion, often dubbed the Big Freeze or heat death. Imagine a party that just keeps going, but eventually, all the snacks are gone, the music fades, and everyone slowly drifts off to sleep. That's a bit like our universe's potential future. The galaxies, already racing away from each other at an ever-increasing pace due to something called dark energy, think of it as cosmic anti-gravity, will continue to do so. Eventually, they'll be so far apart that even light, the fastest thing we know, won't be able to bridge the gap between them. It'll be like trying to have a conversation with someone on a different planet, impossible. As time marches on, stars will begin to wink out. The fuel that powers them, hydrogen and helium, will be used up. It's like a car running out of gas, it just stops. The universe will become a much darker, colder place. Even black holes, those voracious cosmic vacuum cleaners, aren't eternal. They are thought to slowly evaporate over unfathomable timescales through a process called Hawking radiation, emitting faint whispers of particles until they too disappear. So, no more dramatic cosmic spectacles, just a gentle, gradual fading into nothingness. This process isn't happening overnight, mind you. We're talking trillions upon trillions of years. For us, it's effectively eternity. If you're worried about the lights going out, don't pack your bags just yet. The universe has plenty of time to offer. Some scientists even ponder more exotic possibilities, like a big rip, where dark energy becomes so powerful it tears apart not just galaxies, but atoms themselves. That would be a rather messy, albeit spectacular, end. But for now, the slow, quiet fade to black seems the most likely curtain call for our grand cosmic play. The fate of stars. The life of a star is a dramatic journey, far from a quiet retirement. It all begins with a cosmic ballet of gas and dust, a nebula, that collapses under its own gravity. This collapse heats the material, and if enough mass gathers, nuclear fusion ignites in the core. It's like a tiny, perpetual explosion, powering the star for millions or billions of years. Our Sun, a rather average star, has been happily fusing hydrogen into helium for about 4.6 billion years, and it's got plenty of fuel left for another 5 billion or so. Think of it as a giant, celestial gas guzzler, but one that produces light and heat instead of exhaust fumes. But what happens when that stellar fuel runs low? For stars like our Sun, the end is a bit of a show. As hydrogen in the core dwindles, the star starts to puff up, becoming a red giant. It swells so much that it could engulf its inner planets, so, sorry Mercury and Venus, you're probably toast. Then, the outer layers are gently shed, creating a beautiful, glowing shell of gas called a planetary nebula. What's left behind is the star's core, a dense, hot remnant called a white dwarf. This stellar ember will slowly cool over an unimaginably long time, eventually becoming a cold, dark cinder, a black dwarf, though the universe isn't old enough for any of these to have formed yet. For stars much more massive than our Sun, the ending is considerably more explosive. They burn through their fuel much faster, living fast and dying young, in astronomical terms. When their core runs out of hydrogen, they fuse heavier elements, and this process continues until iron is formed. Iron fusion doesn't release energy, instead, it consumes it. This causes the star's core to collapse catastrophically in a fraction of a second. The outer layers then rebound off this imploding core, creating a spectacular supernova explosion. This blast is so powerful it can outshine an entire galaxy for a brief period, scattering heavy elements forged in the star's heart, including those that make up our own bodies, across the cosmos. The remnant of a supernova depends on the star's initial mass. If the star was only moderately massive, the core collapse can leave behind a neutron star. These are incredibly dense objects, packing more mass than our Sun into a sphere only about 20 kilometers across. Imagine squeezing Mount Everest into a sugar cube, that's the kind of density we're talking about. If the original star was truly colossal, even a neutron star can't withstand the immense gravitational forces. The core collapses further, creating a black hole, an object with gravity so strong that nothing, not even light, can escape its pull. These cosmic vacuum cleaners are the ultimate end for the most massive stars, a silent testament to the universe's most extreme physics. The fate of galaxies. Galaxies, those majestic islands of stars, gas, and dust, are not eternal fixtures. Their ultimate destinies are written in the cosmic script, largely dictated by the relentless expansion of the universe and the ever-present pull of gravity. For now, many galaxies are on a collision course. Our own Milky Way is on a slow-motion collision course with the Andromeda Galaxy, a cosmic dance that will culminate in a spectacular merger in about 4.5 billion years. Imagine two massive cities merging, street by street, building by building, but on a scale so grand it encompasses billions of stars. It won't be a sudden smash-up, but a gradual intermingling, with stars themselves rarely colliding due to the vast distances between them. Instead, the gravitational tides will warp and distort both galaxies, eventually forming a single, larger elliptical galaxy. But what about the universe's expansion? This cosmic stretching, driven by something scientists call dark energy, is a powerful force. If dark energy continues to dominate, it could lead to a scenario known as the Big Rip. In this extreme future, the expansion would accelerate so much that it would eventually tear apart galaxies, then stars, planets, and even atoms themselves. It's like a rubber band stretched so thin it snaps, but instead of a rubber band, it's the fabric of spacetime. This is a rather dramatic end, and current observations suggest it might be the most likely outcome, though other possibilities remain. Another potential fate for galaxies, particularly in a universe where dark energy eventually weakens or even reverses, is a big crunch. In this scenario, the expansion of the universe would halt and then reverse, with all matter collapsing back into a single point. Galaxies would rush towards each other, merging and coalescing into an ever denser, hotter mass. It would be the ultimate cosmic traffic jam, but on a scale that would make any rush hour on Earth seem like a leisurely Sunday drive. This outcome is less favored by current data, but it's a fascinating theoretical possibility that highlights the dynamic nature of our universe. Even if galaxies avoid a dramatic big rip or big crunch, they face a slow, inevitable fade. Over trillions of years, star formation will cease as the gas and dust needed to create new stars are depleted. Existing stars will burn out, becoming white dwarfs, neutron stars, or black holes. Galaxies will become dimmer and dimmer, populated by stellar remnants and perhaps a growing population of wandering black holes. It's a quiet, gradual decline, a cosmic twilight where the vibrant lights of starbirth are replaced by the lingering embers of stellar death. The universe will become a much lonelier, darker place, a testament to the transient nature of even the grandest structures. The ultimate fate. The universe, it turns out, isn't destined for a cozy, eternal warmth. Scientists are pretty sure it's heading for a deep freeze, a scenario often called the Big Chill or heat death. Imagine a party that slowly, inevitably, runs out of music, snacks, and eventually, people. All the energy that makes things happen, like stars shining and galaxies spinning, is gradually spreading out. This spreading is like trying to keep your house warm on a super cold day with all the windows open. The heat just escapes, and eventually, everything gets cold. This isn't happening overnight, of course. It's a process that will take trillions upon trillions of years, far longer than we can truly comprehend. Even our sun will eventually burn out, becoming a white dwarf, and then a cold, dark cinder. Other stars will do the same. Galaxies will drift apart, their cosmic dance slowing to a crawl. Even black holes, those voracious cosmic vacuum cleaners, aren't immortal, they're predicted to slowly evaporate over unfathomably long timescales through a process called Hawking radiation. It's like a giant, cosmic game of Jenga where every piece removed makes the whole structure a little less stable. Eventually, the universe will become a vast, empty expanse. The temperature will approach absolute zero, that magical point where all molecular motion stops. There will be no stars, no galaxies, no life as we know it. Just a cold, dark, and incredibly dilute soup of fundamental particles, too far apart and too low in energy to interact in any meaningful way. Think of a library where all the books have been scattered across the globe, and the pages have turned to dust. Information, structures, and activity would cease to exist. This ultimate fate, while perhaps a bit bleak, is a logical consequence of the laws of physics as we currently understand them. The relentless march of entropy, the tendency for disorder to increase, dictates this eventual state of maximum dispersal and minimum energy. It's the cosmic equivalent of a perfectly tidy room eventually becoming messy again, but on a scale that dwarfs our everyday experiences. So, while we enjoy the warmth and light of the universe now, its ultimate destiny is a profound and cosmic silence. The search for a theory of everything. For centuries, scientists have dreamed of a single, elegant explanation that ties together all the fundamental forces and particles in the universe. It's like trying to find the ultimate instruction manual for reality. Think of it this way, you have gravity, which keeps your feet on the ground and planets in orbit. Then there are the electromagnetic forces, responsible for light, electricity, and magnetism, basically, everything that makes your phone work. And don't forget the nuclear forces, which hold atoms together and power stars. The challenge is that these forces seem to behave very differently, especially at extreme scales. Gravity is weak but has an infinite reach, while the nuclear forces are incredibly strong but only act over tiny distances. How can one set of rules govern such diverse phenomena? Physicists have made incredible progress, successfully unifying electricity and magnetism into electromagnetism. Later, they realized that the electromagnetic force and the weak nuclear force, responsible for certain types of radioactive decay, are actually two sides of the same coin, a discovery known as the electroweak force. This was a huge step, showing that seemingly distinct forces could be linked. It's like finding out that a fork and a spoon are just different forms of the same eating utensil. But the big bosses, gravity and the strong nuclear force, which binds protons and neutrons in the nucleus, have remained stubbornly separate from this unified picture. The quest for a theory of everything aims to bridge these gaps. It's the ultimate scientific puzzle, a grand unified theory that would explain why particles have the masses they do, why there are 3 generations of fundamental particles, and how gravity fits into the quantum world. String theory is one prominent candidate, suggesting that fundamental particles aren't point-like dots but tiny, vibrating strings. Different vibration patterns correspond to different particles, and gravity naturally emerges from this framework. Another approach is loop quantum gravity, which quantifies space and time themselves, suggesting they are made of discrete, indivisible units. It's a bit like discovering that the seemingly smooth fabric of reality is actually woven from tiny threads. The implications of finding such a theory are staggering. It could unlock secrets about the Big Bang, the nature of black holes, and perhaps even the possibility of other universes. It would be the ultimate scientific achievement, a testament to human curiosity and our drive to understand the deepest workings of existence. While we haven't found it yet, the search itself has pushed the boundaries of our knowledge, leading to new mathematical tools and a deeper appreciation for the intricate beauty of the cosmos. It's a journey that continues, fueled by the hope that one day, we'll have that single, all-encompassing explanation. And so, from a fiery beginning to the vast, star-dusted expanse we see today, the observable universe has an epic story. We've journeyed through billions of years, from the tiniest particles to the grandest galaxies, all unfolding in a cosmic dance that's still very much in motion. It's a humbling reminder of our place in the grand scheme of things, isn't it? Like trying to count all the grains of sand on all the beaches, ever. But the universe is full of mysteries, and our journey is far from over. What happens when stars, the very engines of the cosmos, reach the end of their spectacular lives? Next time, we'll explore the dramatic and often explosive finales of stars, from dazzling supernovae to the enigmatic black holes they can leave behind. You won't want to miss it.